any of the next days, I'll just video and we'll just practice problems is all we're doing. Alright, so the last one on here, last for the notes, would be buffers. And a buffer system is one that resists a change in pH. That's the whole thing about a buffer. So even though you're adding an acid or you're adding a base, it resists that change to the pH. Okay, here is something they referred to it as on the AP test. A buffer is a sink or a source for protons, and I'm going to put, yeah, just protons. There it is. So it's a sink or a source for protons. Hand me that. This is mine, isn't it? Yes? I didn't just steal yours, did I? That would be rude.
Yeah, it's kind of.
What did you do to it? Come on. Mm-hmm. Is it dead? You can have that one if you want it. Okay, so when I say it's a sink or a source, so when we have a buffer, it's going to be able to suck in the protons, right? That would be a sink. So when we say something's a heat sink, like our lab tables are heat sinks, they can really absorb the heat, right? Yes? Okay, if it's a proton sink, it means it can really absorb the protons. It can also be a source. It can really give up the protons. It's got a lot of protons to donate to that system too. So it's either, depends on how you're using it, it's going to either suck up the protons or it's going to be able to donate those protons that are there. So what this buffer does is it limits how the pH of a solution changes on the addition of an acid or a base. It's another formal way of saying it. It limits how, let me change that. Limits how okay, the buffer limits how the pH of a solution changes. There we go. When you add an acid or a base. So it limits how the pH of a solution changes with the addition of an acid or a base. And it does this by using the common ion effect. Or you create this by using the common ion effect. Okay, do you remember the common ion effect where if we tried to get something to dissolve, let's say we tried to get magnesium chloride to dissolve and it already had some sodium chloride in it, so they both had the chloride ions, and it would mess up how much the magnesium chloride could dissolve in there, right? Yeah? So that's the common ion effect. In this case, let's say we have a weak acid and it's got the acetate ion in it, right? Well, if we have a weak acid and we put a strong base with it, it's gonna change the pH fairly quickly, but then it'll get to a range where it has a buffer zone. We can actually enhance that buffer by adding sodium acetate to it. So if we have acetic acid, hydrogen acid, or that hydrogen ion with the acetate ion, and then we also add sodium acetate in it, every time we release some hydrogen ion, it's going to be sucked up by the other acetate ion, right? Because sodium acetate completely separates into ions in water, right? Hydrogen acetate, if you want to call it that, doesn't completely separate. So if there are any loose hydrogen ions around there, it's going to be sucked up by that acetate ion. Yes? Yes? And so it sucks up more hydrogen ions than it would without that common ion. Are you following me on that a little bit? Okay, so what we can do is we can create a buffer system. So I'm going to use one as an example. I'm going to use an acid. So if we have a weak acid plus its conjugate base, and by the way, its conjugate base is a salt.
Conjugate base will always be a salt.
Yeah, you have two things made, right? When you have an acid-base reaction, you have a water, right? And you have a salt. In this case, its conjugate base is the salt. So let me give an example here. So we have HC2H3O2, and I'm going to write it like it's inorganic. And it's going to split into the H ion plus the C2, the acetate ion, right? Okay, here's the acid, and here is its conjugate base, right? So when we want to make a buffer solution, we would take the acid and add its conjugate base to it. So we might have the acid here, and then we might add sodium acetate to it. So a buffer would be HC2H3O2 plus, let's say, sodium acetate. We want something that separates completely into ions, right? So here we have the acid, and again, this stays in solution. The sodium ion stays in solution no matter what. So it's just floating around in there doing nothing. So basically, we have the acid plus its conjugate base, right there, its conjugate base, that's a buffer system. If any more acid is added, so if we have this system, okay, so look, if any more acid is added to this, let's say we add HCl. Okay, that's a strong acid, right? If we add HCl to this, every time that H is freed up in that hydrochloric acid, every time it's freed up, this guy's going to suck it up and eat it and form H, this stuff, yes? Because in this reaction, right here, it's heavily shifted to the left. It has a really low Ka. It doesn't separate into ions very well at all. So if I have acetic acid plus sodium acetate, that's going to be a weak acid and it's salt. Yes? So I'm going to have it like this. I just got rid of the sodium ion because it's just floating around before and after. It has nothing. It's a spectator ion. Does nothing here. If I now take this piece right here and I throw in some hydrochloric acid, it's not going to change pH very much at all. Because every time this hydrochloric acid, every time it splits into H plus and Cl minus, this H plus is sucked up by every one of those. Because this does not separate well at all, does it? So this guy hooks up with this and takes it out of position. Yes or no? Every time I put one of these in, it splits, but this one is immediately taken out and hooks up with the acetate. So we have HC2, H3O2 together. Because it's got a low Ka, it doesn't split very well in water, it doesn't ionize or dissociate or whatever. So it's going to go back to this. Now I'm left over with some chloride ions. Yeah? So I've got lots of sodium ions floating around, I've got lots of chloride ions floating around. Every time I put another one in, it's going to be sucked up with this extra. Because this is not going to hook back up with the sodium. They're completely soluble in water. They separate into ions, but it is going to be sucked up with this one because it doesn't. You can think of it as being not soluble in water. Does that make sense? And kind of thinking it that way too? That's what a buffer system does. So that when you have the original acid and its conjugate, or you can say the original acid and its salt, they'll say, I've seen them both ways on the test, what it acts like is a buffer. Because if you have a weak acid, it splits a little bit, but really not a whole lot. And if you throw in its salt, well, this is going to split from each other, but any extra hydrogen ions you put in there is going to be sucked up by this. There's your hydrogen ion sink. So a buffer system acts as a sink. In this case, this is acting as a sink for it. It means it just soaks up those hydrogen ions. Now, can it be overwhelmed? Yes. You keep adding enough hydrochloric acid, and that pH is finally going to kick over that. You're going to have used up. When you used up all this stuff right here from the sodium acetate, then it's going to increase in pH pretty quickly. To find the pH of a buffer system, use the Henderson-Hasselbalch equation. If I were you and they gave you a buffer question on the AP test, I would save it to the last. I might skim through there and see if there's something I could answer really quickly, but I would save the rest of it to the last because it's going to be a little bit more time intensive. So to find the pH of a buffer system, use the Henderson-Hasselbalch equation, which is here. That's the one. So pH equals pKa plus the log of the anion over the total acid concentration. Yeah. And then you could do the same thing if you want pOH. You could just replace that with B's. And the hydroxide ion concentration, yeah. But I'll tell you, the vast majority of real-world questions would be with the pKa, would be with the acids, because the vast majority of our foods that we eat are going to be acidic. And so we spend a lot of time with we spend more time on the acids and the pH and stuff than we do with the bases. Why? Something in my eye here. Okay, now, in this case right here, this little piece is the half equivalence point. And sometimes they'll just point out, they'll point blank give you the half equivalence point, and they'll expect you to know to put it in here. Okay, now, here's the kicker. If these two numbers are equal, yeah, if those two numbers are equal, then the pH equals the pKa. Equals the pKa. And when you're doing a titration, that's at the half equivalence point. Oh, what did I do here? I'm sorry, I shouldn't have written that one down. That's not the half equivalence point. I'm jumping ahead of myself. Erase that part that you just wrote down there. Okay, so if these two are equal, then the half equivalent, that's going to, okay, so if these two numbers are equal, that's what happens at the half equivalence point. So at the half equivalence point, these two numbers are equal, and so the pKa is the pH, right? So that's what it should say. this, what I wanted to put here, sorry, remember this pKa means negative log of the Ka. That's what that means. Sorry, I went into the wrong spot. So this is the half equivalence point. Okay, we have a tiny little bit left to go. Not much though.